You've just been handed a paper. You look at the methods section and you see the words, randomized controlled trial. You nod. You continue reading. But do you actually know what that means? Do you know how that study was built, why the researcher chose that design, and what it can and cannot tell you? Most dental students can name study types. Very few understand how they work from the inside. By the end of this episode, that changes. We're going through every major study design you will encounter in the dental literature. For each one, you'll know whether it's observational or interventional. You'll know how it's performed, what it aims to answer, what you can extract from it, and where it can mislead you. Before we start, we need to understand the two worlds every study lives in. In an observational study, the researcher is a witness. They do not interfere. They do not assign treatments. They observe people as they exist in the real world and record what happens naturally. Think of a wildlife photographer. They capture what is already happening. They do not move the animals or create the scene. In an interventional study, the researcher is an actor. They step in and change something deliberately. They assign a treatment, create two groups, and measure what happens because of that change. Think of a chef running an experiment. Two identical kitchens, one ingredient changed, everything else the same. Some designs can live in both worlds. We will flag this as we go. Now, the pyramid, from the bottom up, the case report. A clinician sees something unusual. They document everything, history, findings, radiographs, outcome, and publish it. One patient, one finding, observational only. The aim, to say this happened, and the world should know. What you obtain, a clinical description and a hypothesis. The limitation, one data point, no comparison, no generalization. Real example, the first descriptions of bisphosphonate-related jaw necrosis came from case reports. Before those papers, no one had made the connection. That single observation changed prescribing protocols globally. The case series, same concept as the case report, but now you have a group. 10 patients who develop peri-implantitis after using the same implant surface. 15 patients with unexpected soft tissue recession after a specific suturing technique. The researcher collects them, describes what they share, and looks for patterns. Still observational only. Still no control group. Still no randomization. But a pattern across 10 cases is a stronger signal than one. The aim? To describe a clinical pattern and generate a hypothesis worth testing. What you obtain, frequency data within the group, shared characteristics, a foundation for a future controlled study. The limitation, no comparison group, no causation, prone to selection bias. Real example, a surgeon documents 20 consecutive patients who received immediate implant placement in fresh extraction sockets. All 20 maintained bone levels above the threshold at 1 year. Promising, but without a control group, you cannot conclude it is better than delayed placement. The cross-sectional study. This is a snapshot. You take a population, look at them at one specific moment in time, and measure something. Almost always observational, rarely interventional. How it is performed. The researcher defines a population, sets inclusion and exclusion criteria, recruits participants over a defined period, and at a single point in time measures both the exposure and the outcome simultaneously. One visit, everything measured at once. The aim, to measure prevalence. How common is this condition in this population? To explore associations between two variables. What you obtain, prevalence data, association data, a snapshot of a population's health at one moment. The limitation, you cannot establish which came first, the exposure or the outcome. This is called the temporal problem. You see the photograph, but you don't know the story before it. Real example, a researcher examines 600 patients in Kuwait in a single visit. They record periodontal status and ask about diabetes diagnosis and glycemic control. Result: Patients with uncontrolled diabetes had significantly higher rates of severe periodontitis. This cannot tell us whether diabetes caused the periodontitis or the reverse, but it establishes a strong association worth investigating further. The Case Control Study. This design is clever. It starts from the outcome and works backward, always observational. How it is performed. Recruit two groups: the cases, people who already have the disease; the controls, people who do not, matched for age and gender. Then look back at the history of both groups and compare their past exposure to the risk factor. The aim: to identify risk factors for disease. Especially useful for rare conditions or outcomes that take years to develop. What you obtain: an odds ratio. How much more likely were the cases to have been exposed compared to controls? The limitation: recall bias. Participants rely on memory, and cases may remember differently from controls. You also cannot calculate incidence or prevalence, only the odds ratio. Real example: 80 patients with peri-implantitis versus 80 patients with stable implants. Review of records shows cases were 4 times more likely to have been smokers. The odds ratio for smoking is 4.1. Smokers had 4 times the odds of developing peri-implantitis in this sample. The Cohort Study. This is where we add the dimension missing from every design we've covered so far: time. And here is what makes the Cohort Study unique. It can be either observational or interventional, depending on how the researcher sets it up. In an observational cohort, the researcher selects a group based on a naturally occurring exposure. They smoked or they didn't. They received a specific implant system because their surgeon chose it, not because the researcher assigned it. The researcher follows them forward and records outcomes without intervening. In an interventional cohort, the researcher assigns a treatment to a group and follows them forward, but without a randomized control group. Everyone receives the same intervention. Outcomes are tracked over time. How it is performed. Define the cohort at baseline. Record exposure status or assign the intervention. Follow them prospectively with regular clinical assessments, or retrospectively through existing records. Compare outcomes between groups, or describe outcomes in a single treated cohort. The aim: to establish temporal relationships, to show that the exposure came before the outcome, to calculate incidence, to study long-term outcomes of a disease or treatment. What you obtain: relative risk. How much more likely is the outcome in the exposed group? Incidence data, long-term outcome data. A stronger argument for causation than cross-sectional or case-control designs, because you know what came first. The limitations: expensive and time-consuming. Loss to follow-up is a major threat. If the sicker patients drop out, outcomes look better than they truly are. Confounding variables can still explain results in observational cohorts. In interventional cohorts, without a control group, you cannot know whether the outcome would have occurred without the treatment. Observational cohort example. A research group follows 300 patients who received implants in 2015, 150 smokers and 150 non-smokers, with annual assessments for 10 years. Result: implant failure occurred in 19% of smokers versus 6% of non-smokers. The researcher did not ask anyone to smoke. They observed what happened naturally over a decade. Interventional cohort example. A surgeon places implants using a new surface technology in 80 patients and follows them for 5 years with annual radiographic assessment. Survival rate at 5 years, 97.5%. Marginal bone loss, 0.4 millimeters on average. A treatment was applied and outcomes were tracked, but there is no randomized control group. You know what happened. You don't know what would have happened without this specific surface. The randomized controlled trial. We cross from observational into interventional territory, and we do not come back. The RCT is the gold standard for one reason: randomization. You don't let nature decide who gets what. You decide, randomly. And that single decision changes everything. How it is performed: define a clinical question in PICO format. Recruit participants who meet strict inclusion and exclusion criteria. Randomize them into groups using a method that removes human bias entirely. A computer-generated sequence, sealed opaque envelopes, or a centralized randomization service. The intervention group receives the treatment. The control group receives a placebo, no treatment, or the current standard of care. Where possible, apply blinding. The participant doesn't know which group they're in, single blind. The outcome assessor doesn't know either, double blind. This removes psychological bias from both sides. After a predefined follow-up period, outcomes are measured by a calibrated examiner and analyzed according to a pre-registered statistical plan. Think of the RCT like this. You have two identical patients, same age, same disease, same habits. You flip a coin. One gets the new treatment, one gets the old treatment. You wait. You measure. The coin flip is the key because it means the two groups are equal before you even start. Any difference you see at the end can only be explained by one thing: the treatment. He aimed to prove that a treatment works, not just that it's associated with a good outcome, but that it actually caused it. What you obtain, a direct answer. Does this treatment work better than the alternative? Yes or no? The limitations. The patients in an RCT are carefully selected. They may not look like your real patients in the clinic. The study might run for 6 months, but you'll be using this treatment for 20 years. And some questions can never be randomized. You cannot randomly assign people to smoke for a decade to study bone loss. Real example: 160 patients with severe periodontitis. Half received deep cleaning plus antibiotics. Half received deep cleaning plus a placebo pill that looks identical. Nobody, not the patient, not the examiner, knows who got what. After 1 year, the antibiotic group showed significantly better results. That result can be trusted because everything else was equal. The systematic review and meta-analysis. The top of the pyramid. Unlike every other design we covered, this is not a study of patients. It's a study of studies. Imagine you want to answer one question. Does adding antibiotics to periodontal treatment actually help? There are 50 studies on this topic. Some say yes, some say no, some say maybe. How do you make sense of all of them? You do a systematic review. You collect every study ever published on this question. You filter out the weak ones. You keep only the high-quality ones. Then in a meta-analysis, you combine their numbers into one single answer that is more powerful than any individual study alone. How it is performed. Write a precise PICO question and register it publicly before starting. Search every major database: PubMed, Cochrane, Scopus. 2 independent reviewers screen every result. Studies that pass the quality filter are included. Their data is extracted and pooled into a statistical model. The result is shown as a forest plot, a visual that shows every included study and the combined conclusion. The aim: to give the most reliable answer currently available to a specific clinical question. Think of it as asking 50 experts the same question and combining their answers into one. What you obtain: a pooled result more powerful than any single study, a map of what we know and what we still don't. The limitations: garbage in, garbage out. If the included studies are weak, the review inherits their weakness. If the studies are too different from each other, different patients, different protocols, different follow-up, combining their numbers may mean nothing. Real example: a Cochrane review asks whether systemic antibiotics improve attachment levels in periodontitis patients compared to scaling alone. After screening thousands of abstracts, 45 RCTs are included. The pooled result shows 0.3 millimeter additional attachment gain with antibiotics, statistically significant. But is 0.3 millimeter clinically meaningful in your practice? The authors say, modest benefit, moderate evidence, use selectively. That is the complete pyramid, every study design you will encounter in the dental literature. Two worlds, observational and interventional, each one with a purpose, a method, a strength, and a limit. Let's bring it all together in one sentence per design. Case report, one patient, one finding, the first signal of something the world hasn't seen yet. Case series, a group of similar cases, a pattern starting to take shape, but still no comparison. Cross-sectional study, a photograph of a population at one moment in time, good for prevalence, weak for causation. Case control study, start from the disease, look backward, find what was different in the history. Cohort study, follow people forward through time, watch what happens, establish what came first. Randomized control trial, flip a coin, control everything, and finally answer whether a treatment actually works. Systematic review and meta-analysis, collect the best studies, filter the weak ones, and combine the evidence into the most powerful answer science can currently give. 7 designs, 2 worlds, 1 pyramid, and now you know where every paper sits on it. This is your filter. Every paper you read from now on, identify the design first, before the title, before the abstract, before the conclusion. Because the design is the lens, and now you have it. Next episode, the title and the abstract. How to read 60 words and know whether a paper deserves the next 20 minutes of your time.